And then there's a place down here, start video. Should I push start video?
Yeah, I just sent the announcement.
Okay. I'm going to click on start video. Hey, there I am. There's me with the whiteboard in the background. We made it. We made progress. We did great. There's the whiteboard.
Okay, I sent it, Dad.
Thank you. I think they'll start logging on here. Let's see. Let me see if there's any participants. Manage
There probably
participants.
isn't yet. I just sent it.
Oh, okay. I don't see any participants yet, but I bet I will. But it looked like at 1 o'clock I'm scheduled.
Yeah, I don't know what happened. I'll have to look at that.
Yeah. I don't know what
Okay,
happened.
well, I'm going to try to log into it and see if I can see the meeting.
Okay. Well, if they'll show up, I can have a class.
Well, I would go ahead and do it even if they don't show up. That way you can record it and send it to them.
Hey, that's a good idea. Good idea.
Yeah, I just logged in, so as long as they look at their announcement.
Yeah.
You need to move your board over. Your head's in the way.
Okay. Well, I'll just move my head out of the way.
Or move the computer.
Move the computer. Which way?
Other way. And then tilt the board down a little bit.
Like that?
No, not the computer. Tilt that back up. Tilt the board itself.
Oh, the
down
board.
A little bit.
Tilt the board. How's that?
Now scoot the computer over to, I guess it'd be your left.
Scoot the computer over to my left. Like that?
Yeah, a little bit more.
Like that?
Yeah.
I'll move my chair back a tad. Okay. There. Well, I don't see the board.
Well, did you pin yourself?
No. Here,
Okay, well,
I'll pin myself. Okay. There. How's that? Okay.
Well, I would just wait and see. You can't see you, but now you can.
Yeah.
I would just wait and see if they log in, and if they don't log in, then just do your class like normal.
Okay.
Recording.
I will.
All right.
Thank you.
Bye.
Bye.
Love you. Bye.
I love you. Bye.
I'm going to see this back at the technician. 72 Southview.
Well, let's see. Today is the 20th, Monday the 20th. Okay. Well, I sure wish I could get some students logged in. Says here, message, manage participants. Nobody has logged in. It's 9:30. Well, I guess we'll go ahead here and have our dynamics class, even though nobody's logged in. Okay. Let's see what we're going to talk about today. Well, you had some homework that's due today. We probably should talk about that. That might be smart. It was, I think it was 1779 or 1770. Yeah, it was 1778. I'll tell you what, let's do 1779 while we're waiting for some people to log in here, because it's just like the one you were supposed to do for homework. And it's a good problem. Let me find it here. 1779. Yeah, there it is. Okay, when you're doing these problems, you have to do two free body diagrams. So I'm going to draw them now. Here it goes. Now A is 5 kilograms, and it really, that's a pretty lousy circle there, you know. A should be down here. 5 kilograms. And B should be up higher here, and it's bigger, and it's 10 kilograms. And then this is 3 kilograms, right? Yeah, 3 kilograms. And the radius is 0.15 meters. There we go. Okay, what else do we need to know? Well, that's enough. Let's play with that, shall we? Well, first of all, let's get the moment of inertia of the pulley. And if you look in the flap of your book, that's the formula, 1/2 mr squared. Look in the flap of your book. I see it. It says 1/2 mr squared. There it is. It's the last page of your book. Okay, well, let's get it. Oh, gee, here's my calculator. 1/2 times 3 times 0.15 squared. I'm getting 0.09375 kilogram meters squared. Okay. But now we're not done. We got to draw 2 free body diagrams. Well, what's going to happen if you don't draw 2 of them? Well, you don't get your 4 points. You get 3 points maybe. So we're going to do it right. Remember, one is for the forces, and the other one is for the kinetic forces. One is for the moments, and one is for the kinetic moments. This 3 kilogram thing, why did I write that there? This is 10 kilograms here. Okay, now on this one, Well, we're not through with this one here. Hey, I got some red, my wife got me some red pencil here. Look at here. We're going to put some red on here. Haven't I told you you're supposed to put your forces in red? I can do this one in my head. This one's 98.1 newtons. Does that come out? Gosh, that doesn't come out very good, does it? Forget it. Red doesn't come out too good. Never mind. We'll just put it in black. What the heck? That's 98.1 newtons, but you can see that, I think. And this one is, I can't do that in my head. It's 49 something. Let's see. 5 times 9.81 is, it's 49.05 newtons. There we go. Now, there's also a force here, guys, and a force here. Yeah, I kind of got in the way of my M there for meters, didn't it? Now I can tell you what that one is. I think I drew it awfully long. It's 3 times 9.81. 29. This one's 29.43 newtons. Now this one's going to be, it's going to be longer than 29.43. See, that's just the weight of the pulley. But this is the support that's holding the pulley. And it's got to carry these two. But don't be fooled. It's not equal to these three added up. See, if you add those three up, what you'd get would be 29.43, 98.1, and 49.05. Now, if you added all those up, what you would get would be 29.43, 98.1, 49.05. You'd get 176.58, but you're going to discover that, call it F, okay? F is not equal to that. We'll call this force F. F is not going to equal that because in this class, the sum of the forces is not zero. In this class, the sum of the forces is equal to ma, mass times acceleration. It's not equal, the sum of the forces is not equal to zero. See these forces going down? There's three forces going down. I added them up, I got 176 something. If the sum of the forces was added up to zero, then this force here holding the pulley up would be 176.58, but it's not, because the sum of the forces is not equal to zero in this class. It's equal to ma. Now on this diagram here, you're going to have an I alpha. They have a name for that. It's called kinetic moment. It's a kinetic moment. Now you also have, this here is going to be going down, and it's equal to ma. And that's a kinetic force. See these here, I put a red arrow here, but it didn't show up. Never mind, red didn't show up. That's a force. That 49.05 is a force. This is a kinetic force. And this also has a kinetic force. But here's the tricky thing about that kinetic force. It's not going down it's going up. That MA is going up because it's going up. See, that's the 5-pound deal. It's going up. This kinetic force is going down, and that kinetic force is going up. And this is a kinetic moment. Okay, we've drawn our two diagrams, and now we're going to write our equation and solve for everything. Here we go. The sum of the moments acting on our system is equal to the sum of, we're going to take them about this point here, call it, I hate to call it G, because it is not the center of gravity of our whole system. It is the center of gravity of our pulley, but this system consists of a pulley and a couple other masses. The center of gravity is not there. But nevertheless, I'm taking the sum of the moments about that point, G, and I'm getting, well, see, these two don't give you a moment. They go through the point. But you do get a 98.1, 98.1 newtons times 0.15 meters minus, see, that's clockwise. We're writing everything clockwise. Minus the 4905 times 0.15. And by Jove, that's it. For the moments on the left, now there's an equal sign. Now on the right-hand side of Newton's second law, you have the kinetic moments. So what you'll have is I alpha. Now there's the I, so let me write that. You'll have 0.09375 kilogram meter squared times alpha. And then you have these kinetic moments. Now a kinetic moment goes like this. See, these are kinetic forces here. And when you take R cross MA, you have a kinetic moment. Okay, now this kinetic moment here will be plus R times M, which is 10, times A. Now A is equal to 0.15 alpha. See, A is equal to R alpha. But we're not done yet. See, that's clockwise. All these are clockwise. But this one will be clockwise too. Oh, I'm running out of room here. But that one's going to be 0.15 times 5 times 0.15 alpha. And oh, look, you have a nice equation now with only one unknown. Okay, I'm going to solve for alpha now. Here goes. Well, hey, you do it. Why should I do all the work? You do it. You solve for alpha. And let's see if, I think I have the answer here someplace. Here's what I got. When I solved for alpha, I got 19.8 radians per second squared. Now, just to make sure I'm not lying to you, I'm going to plug that in and see if that's what I get. Well, that's not what I got this time, but I like to do these 2 or 3 times before I give up. So let me try again. Here goes. I'm trying again. No, I keep getting a different answer. I get 17061 something. I did that twice in a row. So I must be doing something wrong. Let me check my stuff here. Let me make sure I got this moment of inertia correct. Ah, that's my problem right there. This is wrong. So let me do that over again. Just a minute now. Some of you probably already caught that. This is wrong. It's 0.03375. So this was wrong. We're gonna fix it. What the heck happened? What? Okay, I think I'm back on track now. All right, now that was wrong, so we're going to fix it. Made a mistake there. It's 0.033, blah, blah, blah. So this is 0.033, blah, blah, blah. Now we're going to get the right answer, and I think that is the right answer. I just had the wrong moment of inertia. But I'm going to double check it to make sure. Here goes. I'm double checking it now. Point 0.03375. Boy, Jove. That's right. I think it's 19.82 radians per second squared. And I think we're back in business. And now we can get the acceleration of either body. One of them's going up and one of them's going down. You just go alpha R, and R is 0.15. Do that, and let's see what we get. I'm getting a 2.97 meters per second squared. Now let's see how we did. We're going to look at the answer book now and see what they said. But then I'm not through. I'll show you some more things about this problem. And I know you can do your homework a lot better now. But I'm going to look up this 1779 now. And it says 1779. It says 2.97. That's what the answer book says. 2.97 meters per second squared. So we successfully did that problem. I goofed up on the moment of inertia there somehow, but we're okay now. Now, just for fun, let's find the tension in this cable. I don't think we ever did the tension in the cable. Ooh, wouldn't that be fun? Yes, it would, Dr. Griffin. I just need a little room to work with. Let's see. Not much room there. Where can I do that? Well, hey, there's some room up here. We'll just erase this word dynamics. And we'll write Newton's second law on on this body here. Now this body here is going to go up. And so it has tension minus the 4905 equals 5 kilograms times 2.97 meters per second squared. Hey, we can solve that and get the tension. And now watch out now. The tension in this rope and the tension in that rope could be different. Dun, 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 dun. They could be different because, see, the pulley has inertia and it makes a difference. Okay, here goes. We're going to find that. They didn't ask for it. This is just for fun. Let's see. Well, maybe I'll ask you something like this on your final. Ooh, okay, 5 times 2.97 plus 4905. Ta-da, I got an answer. The tension in this rope here is 63.9 newtons. Now let's get the tension in this other rope. Okay, here we go. Now the way that works is, well, see, that one's going down. I think I'm going to write my equation going down. So we got 98.1 newtons minus the tension going up equals 10 kilograms. And now it has the same acceleration because they're connected. So we're going to solve that. Here we go. We'll get the tension in that rope. All right. 98.1 minus 29.7. Okay, here's what I'm coming up with. The tension in that rope is 68.4 newtons. Let me write that. See this rope here? The tension in this rope here is 68.4 newtons. Hey, it's bigger. The tension in it, you know, that kind of makes sense if you think about it. For this thing to spin, for it to spin clockwise, it's going to spin clockwise. Wouldn't you have to have more tension on this rope than on that rope? If they were the same, think about it. If the tensions were the same, it wouldn't spin. By Jove, the tension has to be bigger on this side than on this side for the rope to spin. How come earlier, a couple of months ago, we worked problems where the tension was the same? Well, those problems didn't have, the pulleys didn't have any mass. They were massless. They didn't have any inertia. See, when they have inertia and you want to get something that has inertia to start to move, it's going to take more force yanking on the right-hand side to get it to start to spin because it's got inertia. Now I want to show you one last thing on this problem, then we'll move on to other exciting things. Gosh, I wish I had some customers though. I'm looking here at the message participants. What happened to all you guys? It is Monday, isn't it? I don't have anybody, nobody. Well, you're just going to have to look at this on, I know what you're doing. You guys are taking a nap. You're sleeping in. You're sleeping in, and you're going to watch the show later. That's what you figure. Well, okay, watch it later then. Let me show you one last thing on this problem. For those of you that just tuned in late, I am doing problem 1779. It's just like one that you're supposed to do for a grade called 1778, which is due today, I think. But I want to show you one last thing. I talked to you about this force F here, and I tried to tell you that that force is not equal to the sum of those three forces. I tell you what it is equal to, though. It's equal to that force, and that force, because the pulley is not accelerating linearly. The sum of the forces on the whole system is not zero, but the sum of the forces just on the 3 kilogram pulley is zero. Now, do I have room to write that? Not much. Here, let's just write it here. We'll sacrifice a little room here. I'm going to find this force for you. You still have the 2943 of the weight of the pulley, but see, the tension is 63.9 on the left and 68.4 on the right. Now I'm going to add those up. Here goes. That's going to be F. 29, 43, 63.9, 68.4. Okay, guys, I'm getting 161.73 newtons. See that F there? I'll circle it. It's 161 points. It's not 176, it's 161. How come? Because the sum of the forces on the pulley is on the pulley is zero. But the sum of the forces on the whole system is not zero. Because the whole system has an acceleration. See, look at here. The sum of the forces on the whole system. Can you guys see that? Does that show up? Yeah, that shows up. The sum of the forces on the whole system is equal to ma. And it's bigger than that because you have a net acceleration of your system going down. The 10's bigger than the 5, and it's accelerating down. I know it's accelerating up, but you have an excess of 5 kilograms accelerating downward. And that's how come the sum of the forces is equal to that. Okay, there's that one. And now I would ask if any of you had any questions on this problem, if there was anybody out there. But for some reason, my whole class is bagging Z's this morning. They are not here. Let me check the message participants. And I don't know what happened to you guys. Maybe you figured that we didn't have a meeting. Okay, well, we're going to say goodbye to this problem. If you're happy, I'm happy with it. And then we're going to do something else. All right, say goodbye to the problem. There we go. Well, what wasn't that fun? Oh, yeah, Mr. Griffin. Yeah, it was fun, all right. Okay, well, now what are we going to do now? Well, I wanted to do this one here. What am I going to give you for homework? Now, let me think about that for just a minute. Oh, you know what? We're supposed to be in chapter 18. Well, maybe I can sneak into 18. It's only 10:05 on my clock. We'll see. Yeah, I'll give you some homework before we leave. All right. But right now, what I want to look at is, okay, yeah, this one. Now, this is, we talked about this in a lot of detail. I'm pretty sure we did. It's 1796, 97, 98. It's on page 464 in my book. But what I want to do is I want to do it a little different than they did it. Okay. Well, got to draw 2 diagrams. Those of you that don't draw 2 diagrams, you don't get 4s. That's just tough beans. Okay, here we go. Here's this one. Now this has a, it's a spool. So it has an inside axle, I guess you call it. Has an axle. Now we got to draw 2 of them. Here's the other one. And it has the inner axle. Now this distance here is 0.25 meters. And this distance here is 0.4 meters, and that's G. And this is A. And you have this thing rolling. We're going to do rolling. There's A. There's G. There it is. There we go. Okay. I think we've talked about some of these. We've either done some or all of those, but I'm not doing any of those. I'm changing it, and I'm going to put the force. We could have 50 newtons, but I'm going to put the 50 newtons down here. I'm going to wrap the string or the cord around that way and have my 50 newtons there. Now you also have the weight of the thing, which is 100 grams. Well, that's not weight, that's mass. So the weight would be 981 newtons. And here's your normal force, which would be 981 newtons. Now there's some friction going on, because if there wasn't any friction, it wouldn't roll. I think it would slide or slip. I'm not sure which, but we got to figure out, first of all, we got to figure out which way this thing is going. Well, I think it's going to go to the right. I think it's going to have an MA to the right and an I alpha that's clockwise. And to convince you of that, because I bet there's 2 or 3 of you guys that would vote that it might go to the left as you pull this. It kind of looks like if you pull that, it might spin the other way and go to the left. That kind of makes sense. There's a friction force here. We haven't figured it out yet, but we'll put it in here. We'll call it F. But I have something here to convince you that it's going to go to the right. Now, maybe I can show you this. Yeah, this thing here, you probably have seen these before. If you go to the hardware store, you can get these little guys here. It's a spool. And you know what this stuff is here? This is plumber's tape. You wrap it around the threads. You're going to fix a leaky faucet, okay? And what you do is you wrap that around the threads, and then you screw your faucet in, and it keeps it from leaking. It's plumber's tape. I bet there's 1 or 2 of you out there that have had to fix a faucet, and you know about plumber's tape. But to review here, this problem here, I think, can I show you this? I think I can. This problem here has somebody's pulling on this thing. And when they do, guess what? When they pull on it, it goes, oh, gee. I wish we could have our regular classroom. And I could show you stuff without having to fool with this video jazz. Okay, now here's what I'm going to do. I'm going to pull on this. And when you pull on that, well, of course, it goes to the right. You can see that. I'll do it one more time. What we're talking about is 1796. I think 1796, they just have a spool and they're pulling on it, and by Jove, it goes to the right. Pretty clunky, but that's what it does. Let me read it and see if that's what 1796 is. Yeah. Now 1797, well, you know what? 1798 is the same. It's just they've got a bigger force, that's all. They've got this like this. We're talking 1797. It's just that they're pulling with a bigger force is all. But now, no, 1798 has a bigger force. 1797 is kind of weird. They're pulling straight up. I don't know if you guys can see that, but they're pulling straight up. Okay, let me try that. I know what it's going to do if you pull it straight up. It's going to do the same doggone thing. If you pull it straight up, it's going to go to the right. See, here's what they're talking about. This is what I want to do here in just a minute. But 1796 is when they have the force here, and they're pulling like that with 50 newtons. That's this one here. 1798, I think they changed this and made it real big. I think they made it 600 newtons. Is that what they said? Let me read it. Yeah, they just upped the force, but it's still going to go to the right. Now, 1797, what they're doing is they're pulling. They got the string here, and they're pulling straight up, and I think it makes it go to the right. And we could work those. That would be so much fun. I think I did one of these, if I remember. But what we're going to do today is we're going to take our string here. We're going to put our 50 newtons there. Now, if you do that, I think it still goes to the right, but see our, oh, this is so awkward, but I'm trying. I have a much better deal in a regular classroom. I got a nice big spool that I can show you guys. All right, can you see all that? All right, now I'm going to pull to the right. Here goes. Get my thumb out of there. Look, when I pull to the right, guess what happens? It goes to the right. Let me try that again. When I pull to the right, yeah, I'm going to pull to the right. Here goes. I'm going to pull to the right. Look, it goes to the right. I don't want you to turn. Just go straight, please. All right, pull to the right. See what happens is it's winding itself up. As you pull it, look how long it is here. See how long it is here? Now when I pull it, it's winding itself up. And it's not long anymore. It's wound itself up. Well, I hope that convinced you that it goes to the right. Probably not, but we tried. Okay, and now what? Well, that means it's going clockwise, like I said. And the MA is going to the right. Okay. Can you read my writing here? That's supposed to say a meter. They're 0.4 meters. Now, what we're going to try to find out is what that friction is for one thing and which way it's going. Now, which way do you think it's going? I think it's going to the left, personally. I think the friction is going to the left there because, see, if it was going to the right and this 50 newtons is going to the right, wouldn't the thing spin counterclockwise? So for it to spin clockwise, that friction's got to go to the left. All right, well, we're going to find the friction and we're going to find the acceleration. We're going to find the alpha and the whole ball of wax. So here goes. Since it's rolling, we can write the sum of the moments about point A as IA alpha. Now this equation, remember, I think I told you guys, it's a lovely equation, but it has a skull and crossbones. It only works if you're rolling. If you've got kinetic friction, it's a different ball game. We just have static friction, which is a inequality. Well, we're going to have to get IA in order to do this problem. Here goes. IA is equal to, well, it's not a disk, it's a spool. We don't have a formula for spools, but they give you the radius of gyration. It says it's 0.3. So we can get the moment of inertia. It's just equal to m moment, what they call radius of gyration squared. So what's the mass? Is it 100 kilograms? I'm not sure about that. Let me look that up. The mass is, yes, 100 kilograms. The radius of gyration is 0.3. Hey, I can do that in my head. I'm coming up with, oh, no, wait a minute. Auga. I just about goofed up. The moment about G is equal to that. And it's equal to 9. But the moment about A is equal to the moment about G plus 100 kilograms times the distance between A and G, which is 0.4. I'm using the parallel axis theorem, and I got 25 when I did that. I'm getting a sense of deja vu now. We did that. I think we did that the other day. What the heck happened here? There we go. We did that, and we got the moment of inertia about G and also about A. I ran out of space here, but you know what the units are. They're kilogram meter squared. Okay, now back to our problem. We're going to do the moments about A. Well, these three forces all go through A. They don't give you a moment, but that one does. And it's 50 newtons times what? 0.15. The distance between A and that force is 0.15. And it's clockwise. And this is 25 kilogram meter squared. Hey, we can get alpha now. I wonder why nobody showed up for my class. It kind of bugs me. Have I wandered into an alternative universe here somehow? All right, we're going to get alpha now. Of course, this is clockwise. Here we go. 50 times 0.15 divided by 25. I'm getting an alpha of 0.3. radians per second squared. And now we can get the acceleration, which would be alpha r. Wouldn't that be 0.3 times 0.4? I can do that in my head. I think it's 0.12. 0.12 meters per second squared. I wonder if that's what I got when I worked on this before. Let me see if I did this problem just a second, but I don't remember it. Alpha is 0.3. Okay. I don't know if I ever got the friction, but we're going to get it now. I think we're doing okay. All right, we're going to find the friction. Now here we go. Sum of the forces is equal to MA. We got the A, we got the M, and the forces. Looky here. Going to the right, we have 50 newtons minus your friction is equal to 100 kilograms times 0.12 meters per second squared, right? Right. So, I don't know if I can do that in my head or not. Let me get a drink of water and think about it. I bet I can do that. What from 50 gives you 12? 38? It looks to me like the friction is 38 newtons. Does that work? Boy, Jove, I think it does. We've got the friction now. We've got the acceleration, the linear acceleration and the angular acceleration. Moments of inertia, we did good. But there's one last thing that we always do on our problems. We check our work, don't we? But we're going to check our work and see if that's right. Now, I'll tell you what we've used. We've used this equation here. You know what? We have not used this one. We have not used this equation here. Why don't we do that? And if it works, that's good. That'll be a check on our work. Now, what are the moments about G? Well, you have, gosh, do I have enough room down here? Barely. There's more room up here. You guys don't need that room. Let me have that room. We did that before anyway. Okay, here we go. We are writing the sum of the moments about G equals IG alpha, and we're going to see if it works. It's called checking our work. Okay, and we're going to write them clockwise. So what we got is friction, which we think is 38. That's supposed to be a clockwise arrow there. We have 38 newtons times 0.4 about G minus 50 newtons times 0.15 meters about G equals IG. Now remember, that's 9 kilogram meter squared alpha. We're going to solve this for alpha. Now, if we're very, very lucky, we'll get 0.3. Here goes. 38 times 0.4 minus 50 times 0.15 equals something. Then you divide by 9. I didn't get that answer. Something bad happened. Let me see what I did wrong here. Now, just a minute. 38 times 0.4. Let me try that again. 38 times 0.4 minus 50 times. No, that's wrong right there. See, that's why I need you guys. There's nobody plugged into this thing. That's a 0.25, right? It's 0.25. So let me see if I can do that times 0.25. And you divide by 9. By Jove, I'm getting alpha as 0.3 radians per second squared. Ooh, that's good. Check. We just checked our work. We got the alpha. Of course, with that alpha, you get the same A. And you would get the, everything's great. Now let's double check it. This is called double checking our work. Now there's another equation here that goes like this. I wrote that wrong, but we're going to get it right. Now this equation has a name. And y'all, a little Southern talk, y'all know the name of that equation. And see, I would call on one of you if I had anybody listening to me, but nobody's listening to me. It's Newton's second law for rotation. That's what it is. All right, we're going to plug it in and see what happens. Here goes. Just need a little room here. Moments about A. Well, the friction goes through A. It doesn't give you a moment. This normal force goes through A. It doesn't give you a moment. The weight goes through A. Doesn't. The 50 does. So you have 50 newtons times. That's times the 0.15. Do I need to explain that this distance here is 0.15? I hope not. And that's it, guys. On the right, we have 9 times alpha. What did we say alpha was? 0.3? Plus r, which is 0.4 times 100 times the acceleration of not of gravity, the acceleration of center of mass. Okay, now I'm going to solve this equation for AG. Now, if it comes out to be 0.12, we will have double checked our work. I'm plugging in this equation right here now. It's called double checking our work. Here goes, 50 times 0.15. Then you subtract 9 times 0.3, and you get something. And then what do? Divide by 40? And boy, Jove, I'm getting an AG equals to 0.12 meters per second squared. Oh, that's good. We have just double checked our work. Well, we did that problem. Okay, well, we got a little class time left, and we're going to talk about chapter 18. Are there any questions? Well, no, there's no question because there's nobody there to ask me anything. I don't know what happened today. Say goodbye to this and hello to chapter 18. But you guys can listen to this. It's being recorded, and I believe we'll be able to get it on YouTube. I'm hoping. Okay, turn to chapter 18, and let's see what that's all about. Aha, work energy. Chapter 18, work energy. Oops, didn't mean to do that. This is supposed to be like that. Okay, chapter 18. Work energy. Chapter 18, work energy. Now I need to refresh your memory that they have a secret code for things in this this book. See, the book has their way of doing things, and I have my way of doing things. Now, for instance, if I was going to write kinetic energy, I would go KE. The book goes T. Their secret symbol for kinetic energy is T. I wish they wouldn't do that. If I was going to write work, I would write W for work. Well, the book doesn't do that. The book goes U. I can't help it. That's what they do. Then, by the way, the equation for work we all know and love is F dot, well, ds, dr, some kind of variable there for a distance. It's force times distance. But see, that's translational work. You can also have rotational work. It goes like this. Oh, now how do they write that? They go like this. Where this is a moment times an angle in radians. Instead of a force times a distance, it's a moment times an angle in radians. That's rotational work. I don't know if you've ever had that before. But look at the units. See, that's newtons, that's meters, so you get Newton meters, and you know what that is. We all know and love that a Newton meter is a joule. Now, it's not a bending moment, the wrong class. The moment of a force is a Newton meter, we know that. And angles and radians are nothings. So when we take Newton meters and we multiply by nothings, well, you just get Newton meters, which are joules. But the book doesn't call it W, they call it U for some reason. They don't want too many engineering graduates out there, I guess. Okay, now if you read more in the chapter, they get to potential energy. I think. Let me dig around. Let's see if they do. Yeah, they do. Now, see, if I was going to be writing a book and I wanted to write potential energy, I would go PE. Wouldn't that make good sense? Potential energy. But see, they don't. They write V. If you see V in this book, that's their secret symbol for potential energy. Now that I've given you the secret to the chapter, let me give you some highlights of the chapter. What about homework? Let me give you some homework. Hang on a second here. Now this homework, I'm just learning how to grade homework and catching up. So I'm going to give you a couple of homework problems, but don't turn them in. Do them because you love doing this for me. All right, let me give you some homework here. I need to put this on the, what do they call that? The Blackboard, no, I can't think of the name of it. All right, homework, don't turn in. I'll give you some more turn in homework. Don't worry, we will. But on this one, do these. Now this one is, I like these fundamental problems because they tell you how to do them in the back of the book. And the other one I want you to do is this one. And if you want me to, we can discuss them next time. Yeah, there's your homework. Okay. Content, that's the word. I'll put those on content for you for assignments for you to do. But now let me hit the highlights of the chapter. The most important equation in this chapter, and let's see if I can find it here. It will be the work energy theorem. We've had that for translation, but see, this can include rotation. Aha, there it is. It's on page 480. On page 480 is the most important equation in our chapter. They call it the principle, P-R-I-N-C-I-P-L-E, the principle of, my computer just went bong, the principle of work and energy. That's what we're studying right now. It's chapter 18. And the way they write it is really weird. This is how they write it. I don't like it at all. It's on page 480. Now, see, if I was going to write this, that's the way the book does it. If I was going to write the principle of work energy, which, by the way, is the second most important equation in our course, and you all know, y'all, a little Southern talk, y'all know the most important equation in our course is Newton's second law. Well, this one is the second most important, and the way I would write it is like this. This says the same thing. See, if you take that T2 and you subtract the T1, that's the difference in kinetic energy. And this is their secret symbol for work, the sum of all the works done. So they say the same thing. But don't you like this better? Oh, yes, we do, Mr. Cooper. It makes more sense, doesn't it? I don't like that stinking way they did it. That is the most important equation in this chapter, and the second most important equation in the book. Okay, well, that's some theory. Maybe we should work a problem. I don't know. I don't have much time left, 10 minutes maybe. We could work a problem. Hey, here's one that would be fun. There's a yo-yo. Hey, let's work the yo-yo and then we'll quit for the day. That'll be fun. This is on page 493. Now there's your homework. Let me write that down for you, and we can talk about it next time. Gee, do I have any pencils? Yeah, here we go. All right, I wrote down your homework. But right now we're going to look at a yo-yo. I'm going to erase all this now. I need to put that on content for you. But right now we're going to do 1821, or most of it if I run out of time here. It's a yo-yo. Now, when you do problems for me, how many free body diagrams do you always draw? Well, let's see, 2. You draw 2 of them. So you got this yo-yo here. And we're going to draw 2 yo-yos. And they have a central axis Is that what they call it? Do they call it a central axis? Let me read the problem and see what it says. It's on page 493. Yo-yo weight of 0.3 pounds. Let me write that down. It's 0.3 pounds. Radius of gyration is 0.06. Hey, let me go ahead and get the, that's your point G there. Let me get the moment of inertia about G. It will be, now wait a minute though, don't you have to have slugs? You've got to have slugs, 0.06 feet. That will give you your moment of inertia about G. Okay, well, let me do that. 0.3 divided by 32.2 times 0.06 squared. Did you get 3.354 10 to the minus 5 slug feet squared? We have the moment of inertia about G. Let me keep reading this. It's released from rest. How far must it descend in order to attain an angular velocity of so-and-so? And the R is 0.02. This radius here is 0.02 feet. Okay. Well, let's put the red stuff on there. And I have a red pencil here, but gosh, it just doesn't work very good. Isn't that a shame? See, you'll have a force here going up. Does that show up at all? Not really. Kind of looks black on my screen there. Never mind. Never mind. There's that force there. And then you have a force here of the weight of the thing. What's the weight of it? 0.3 pounds. 0.3 pounds. I don't know what to call this. Call it F, okay? I'm not sure they're equal. I'm not at all sure that those forces are equal because the sum of the forces may not equal 0 in this class. They may equal MA, you know it? So I don't know what that force is, but that's all the forces. I don't see any others. Tell you what, let's make a point A right here. See, here's G. And this point here is A. And let's, I'm thinking that yo-yo is going up, or is it going down? I can't tell. Well, no, it's going down. If you read the problem, it descends. So it's going down. I get the feeling that this force here is smaller than this weight here of 0.3 pounds. And so the thing will go down. Yeah. It's going to go down. So here, look at here. You're going to have an MA going down and an I alpha. I think it's going to rotate counterclockwise. See, these are forces here. The 0.3 pounds is a force. This force here, somebody's got their finger holding it there. It's going up. Those are forces. These are, that's a kinetic force. That MA, they call that a kinetic force. But that I alpha, that's called a kinetic moment. Okay, well, we got that. I think I'll let you guys try to finish that. Let me give you a little more help, and I think we'll adjourn here. We've had a good time, but I'm tired of talking to nobody. Why didn't people show up? Here's the dirty little secret. This thing, it's kind of like a wheel that's got an instantaneous center of zero velocity. That A there, that A right there is the ICZV. It's unraveling about that point, or unwinding, that's the word. It's unwinding about that point. So see, you could use this equation here. It's kind of like rolling. This is the secret to this problem. You can only use this equation for a rolling, or in this case, it's an ICZV. I think I'm going to leave that with you guys. You try it enough. If you remind me, I'll finish this yo-yo problem on our next visit Wednesday at 9:30. I had trouble today. So I say goodbye to all of you. And I'm going to click on end meeting. Here goes. 5, 4, 3, 2, 1, blast off. End meeting for all.